Greetings to everyone. My name is Chinmay Vinay Dandavati. I am currently in the third semester of the MSc Statistics program, which I am pursuing from the Institute of Science Nagpur, which is an autonomous college under the government of Maharashtra. The topic which I have selected to make a seminar or a presentation for this additional activity is linear and multiple regression in R software. So, with respect or in comparison to the topics on which I have made seminars or presentations so far, this again is an outlier to the league of all those topics. Since in the topics which I had discussed so far, they were completely manual in their nature, though I had used R to solve a problem in the presentation on the likelihood ratio tests. But though it was the case in that seminar, still R was a very small part of it. Here somehow R would be a major part of it, and in fact the way of expression or the way of explanation of the concept of linear and multiple regression would be R in this seminar. So before actually jumping to the implementation of this concept or the exercise of this concept of linear and multiple regression in R, I would like to briefly discuss what is the difference between simple and multiple regression. So as the graph suggests very much here, simple regression is the regression where we determine the regression, that is stepping back from the average. Regression here literally means stepping back to the average. So here in simple regression, we have only one dependent and one independent variable. This one independent variable determines how much the dependent variable will regress or will not regress. Whereas in case of the multiple regression, there is one dependent and multiple independent variables, and those multiple independent variables have further correlations between themselves, and this combined effect further predicts if the dependent variable will regress or will not regress. As regards the expression of this equation on graph, so the graph or the plot of simple regression is a simple scatter plot, whereas the graph of multiple regression has partial regression plots where the other predictors or other seemingly less important factors or seemingly less important independent variables, they are somehow adjusted. Now simple regression, as far as the practical implementation or the practical visualization on a graph is concerned, it is nothing but a fitting of a line to a data, a single two-dimensional line to a data. Whereas multiple regression is about fitting an entire three-dimensional plane to a data. It is nothing but adding some additional supplementary data. Now for example, we have to determine the height of a child when he will grow up. Now in the case of simple regression, we can determine whether the child's height will regress, that is, fall back to average, just by using his father's height, where the father's height would be the independent variable and the child's height would be the dependent variable. This dependent variable, that is child's height, would be dependent on the father's height. Now this is an example of simple regression. However, if we go to the nuances of this situation, father's height is one of the important factor to determine the height which the child will gain after she or he will become an adult. However, that is not the only factor. There are many other factors as well. So if we add another factors like the nutrition which the child gets or the exercise which that child does, these would be considered as the supplementary pieces of information which are added as separate dimensions in graph. Each of these factors like nutrition, or the number of hours the child is exercising. Each of these factor would be a separate dimension, a separate plane in this graph. And this sort of determination of dependent variable by multiple independent variables would be termed as multiple regression. Now, after having dealt with what is simple and multiple regression in the real world, now we come to implementing these concepts on a completely different platform than the one we are used to up till now, that is R language. Now, see, when it comes to languages, programming languages like R or Python or Java or C or C plus or HTML, these are languages like the one which we use in our day-to-day conversation. Right now, I am conversing with you in English. You people might be conversing with each other in your native languages, your mother tongues. Conversation is nothing but an exchange of thoughts in our day-to-day conversations. However, in case of programming, it is about giving inputs and getting our work done by that particular software. In case of human conversation, humans are supposed to understand the nuances of the conversations. They are not supposed to have certain prejudices. In a human to human conversation, that is all right. However, this conversation or this communication is between a human and a machine. A machine which has its own set of prejudices, it has its own conditioning, it has its own way of perceiving the things. So, this journey, this presentation would also be uh, an insight as to how the conceivabilities or the perception of the machine or that particular compiler of that R software is. While we converse with each other, we converse in one or the other language. That language has its own grammar, its own vocabulary, its own rules of constructing sentences. Similar is the case with these computer languages as well, where each word, each element of that code, that syntax has some meaning, has some significance with respect to the way in which it is going to be perceived by that compiler. So we will be dealing with how the things work in a much deeper fashion rather than just uh, looking for the ready-made code in some language model like ChatGPT or AI or something like that. So let us begin with this journey. So firstly, I would like to determine the statement of this problem. So we have an example of the data of flowers. We have the volume, the weight, and the length of the petals of 9 flowers, which is as follows. Now our task somehow is to try by the means of our software to compare how well volume is predicted by weight using linear regression, since there is one dependent and one independent variable, as well as how volume is predicted by weight and petal length using multiple regression, since there is one dependent and multiple independent variables. So let us try and perform this on R. So here I would be including appropriate and adequate snippets of the problem, the screenshot of the problem being solved on R, and I would also explain simultaneously some significance of the syntax or the code which is used in that particular that statement of that code, or what it exactly means. And the same would be also the case with the output. So here we begin with our code. We determine the set of data. It is flower dot data, and it has this data frame. Since there is no singular data, it is disseminated into three parts: the volume of the flowers, the weight of the flowers, the petal length. So store, we use this code data frame, we start this bracket, we include this plus volume equals to C. C here denotes the data which is included in this bracket, following bracket. Under the title volume, we add another part of the data, that is weight. We again store it with this C, and we add the final part of the data frame, that is petal length, and we store it under C. And this determines the flower data. We have now successfully stored that flower data for the sake of reference of that compiler. Now, this, as I have said, is the raw data for the flower volume, weight, and petal length. Now, after pressing the enter button, we get this output. As I have said, the compiler has successfully stored this data. It has formed this systematic table where the volume, weight, and petal length are described as separate columns. Now, for linear regression, for the uh, implementation of linear regression, we will be focusing on how well the weight predicts the volume. We would be having one dependent and one independent variable. Now, before doing that, we would also try and plot the graph between these two factors, that is, the volume of the flowers and the weight of that flowers. So we give this command, we start with plot, plot would be the command, we give these brackets, and these are the axes of the graph which we are going to get. We type this command, as soon as we press the enter button we get this graph, and here you can see that the flower weight, the weight of the flower is denoted by the x-axis, and the volume of the flower is denoted by the y-axis. Now, after having achieved this scatter plot, now we need to have some tabulated information, some information in terms of numbers regarding the regression which we have done. So for that we type this syntax simple dot regression lm bracket volume, which is a function of weight, data, that is flower data, and the summary is of this simple regression which we have performed. So here we use lm. Lm is the abbreviation of linear model. It is a function to fit the line to a data. In R, we specify the information as volume, which is equal to the y-intercept plus the slope plus the weight, and thus I had said that volume would be a function of weight. Now volume is specified by weight in the linear regression. R then adds the terms of the y-intercept and the slope by default. R then uses the least squares to find the values of y-intercept and slope that minimize the square residuals from the line. So now the output of this code is as follows. This is a multitude of numbers. So we have to understand as to what this output has to say. Just like we understand what the other person has to say, we also understand what this output has to say and what the compiler has perceived of all which we have given it so far. So here you can see these last two rows are very important. The most important row, and here we have the multiple r squared, we have the adjusted r squared, we have their values as 0.6133 and 0.012 respectively of r squared and p value, and these digits themselves, they describe that the weight has done a pretty good job predicting the size. So now that we have got the result that the weight has determined the the volume very well. Now we have to fit a line of regression into the scatter plot which we had made two slides back. So what would be the code for it? It is AB line bracket open simple dot regression COL equals to blue. Blue would be in double quotes, comma LWD equals to 2 bracket close. Now here simple regression, this first part of this bracket, within this bracket, it shows reference the reference with regards to which this line would be constructed, the context. COL double quotes blue, it would denote the color of the line which would be used to fit that regression, and LWD equals to 2 denotes the thickness of that line. As regards the colors which this R software identifies, so this is an additional information which I would like to give you. It identifies RGB scheme, that is red, green and blue scheme of colors. You can use these three colors, or you can use the hex codes to specify the mix of any of these three colors or the combinations of these colors. So we type this code, and as we press the enter button, we here we, as I have said earlier, we add the line of least square fit to the data, and we change the graph from this to this. Now here you can see we have this line which is blue in color, and it is the line of least square fit to the data. So after having dealt with this, now that we have seen that linear regression fits very well, now we shift to multiple regression. So again, we store the data in the similar form, or if in case you are continuing with the same program, so you need not to again write the same data, you can continue with the same file. But here I have solved both the problems separately, so I have again stored this data separately. I have rewritten it. So here it is. Now here we again consider the raw data for the flower volume, weight and petal length, and we again get this data which is in the form of columns. These are the 9 flowers whose volume, weight and petal length is in the form of columns, stored very well into the compiler. Now in the case of multiple regression, volume would be predicted by weight and petal length. That is, there would be one dependent variable and two independent variables. So as we did in the case of linear regression, here too we would be plotting this data to get a graph of this form. Now if you go a few slides back, while plotting the data for linear regression, I had described the axis. Here I haven't described them. So what the software of R has conceived it has made a graph for all the possible combinations of volume, weight and petal length. And these are all the possible graphs. So in this graph, they denote the axis. So in this graph, you can see we have volume as the y-axis and weight as the x-axis. So here weight and the petal length, they are correlated with the volume and they are reasonable predictors of the volume. In case of this graph, where the y-axis is weight and the x-axis is petal length, we can see that the petal length and the weight are correlated. That is, they provide similar information. If one of them would increase, other would increase. If one of them would decrease, other would decrease. They would provide similar information. They would have similar effect on the data. Thus, we might only need weight or petal length. We only need one of them. So now, after having got this information, now as we did in the case of linear regression, here too we describe this linear model for the multiple regression. So again, we use the same function lm bracket to fit a plane this time to the data since it is multiple regression. So in R, we specify the information as volume, which is equals to y-intercept plus slope 1 into weight plus slope 2 into petal length. Since there are these two independent variables, weight and petal length, which would be describing or which would be predicting this dependent variable, that is volume. That is, volume would be specified by weight and petal length. And R, as it did before, it will add the terms of y-intercept and the slope 1 and slope 2 by default. So now, here we again come to the description of this multiple regression as a linear model. So we again give this command as we did in the case of simple regression. So also we need to get a summary of the regression activity which we have performed. So we get this output, and again it is a very big multitude of numbers and data which we have obtained. So in the case of multiple regression, this particular line, it has something very important or very much functional to say. So it is a comparison of the linear regression which we performed, where there was relationship between one dependent and one independent variable, with the multiple regression where there is a relationship between one dependent and two independent variables. In the case of the second line too, the second row which is of petal length, in this case too, there is the same sort of comparison, and the p-value which we get at the end, it states that using weight and petal length to predict volume is good, but in the row of this petal length, the p-value which we get, that is 0.0219 star. Now star here is a reference to the significance or the p-value of this particular result. Here star denotes 0.01, which is a good value of p, since the value of p is supposed to be less than or equal to 0.05, and this value of p, it is very less, which means that in case of time constraints we can just use petal length to predict volume, and the multiple regression is not significantly better than the linear regression in the case of this data related to flowers. So this was the active result, the functional result which we got after implementing the concepts or by processing the data on R. So here I am at the end of this seminar, and it's the time for acknowledgement. So these are the resources which I have used to design my seminar and to gather the content for my seminar. So I would like to thank you for your patient listening and also for your precious time and your precious attention. Thank you. Thank you very much.